Hello everybody, welcome to MSE100's discussion on electronics. This is part of the MSE100 course in the School of Mechatronics Systems Engineering at Simon Fraser University. So in this brief video, what we're going to do is cover some of the basic components that are used in a lot of the electronic circuits, which would kind of like serve as an introduction to PCB design. The video assumes you don't have too much of a background in electronics, so we're going to go over the really basic stuff. And I'll try for the most part to provide analogies to hydraulic circuits, hydraulics in the sense like fluid circuits in terms of water storage and so on and so forth. So the first component that's useful when we're dealing with electricity and electronics is the actual power supply. So typically the power supply for a circuit comes in the form of battery, or we might actually invert the supply that's coming from the wall and then use it to power all of the electronic components. So the symbol for the DC power supply or battery is shown below. So it has a little longer line which denotes the positive of the battery, and then a shorter, fatter line which denotes the negative of the battery. So this actually acts as a power source and provides the voltage or the potential difference for all of the components that are used in our circuit. So the analogy in terms of the fluids would be of water stored in a tower or a reservoir. So the battery would actually serve as the reservoir of potential energy in our circuit, and then as the water flows, the flow of the water would be analogous to the current in the electronic circuit. So the higher the reservoir, the higher the voltage of the battery, and more the flow from the reservoir, higher will be the current. So the voltage and currents are slightly different components or different ideas. The voltage itself is kind of rather the potential to do some amount of work, and the current is the actual amount of work that's being done. And the product of the voltage and the power would actually give us the product of the voltage and the current would actually give the total power consumed by the circuit. So at this point, even though a lot of the circuits do not actually use alternating current, it's important to mention this because all of the power supplies that are available in the wall are in the form of AC or alternating current. So when you refer to AC or alternating current, what we are actually referring to is a form of voltage which actually doesn't remain constant, rather varies in a sinusoidal fashion. So this is the reason this is adopted, even though it's a little bit annoying for electronic circuits, is that it's easier to transmit AC over larger distances. So if you're really interested, you can kind of Google and search about AC transmission, and they'll tell you how AC can be switched up and down, which is really beneficial when you're trying to transmit over longer distances. Anyway, as far as we are concerned, in North America, the typical power supply from the wall is known as a 110 volt supply, which actually corresponds to a sinusoidal magnitude of 155.56 volts, and the frequency is 60 hertz. So this actually corresponds to an RMS value, which actually measures the equivalent power that's delivered by this circuit or this voltage, and the RMS value for the voltage that comes in the wall is about 110 volts. So most of the DC, what happens is they actually use, most of the components, electronic components use DC. So the first step is to actually convert this AC into a DC voltage that can actually be used in an electronic component. The most common component that you will encounter in a circuit is known as a resistance. Resistance provides, or rather a resistor provides resistance or opposes current, and it's similar to a restriction in the pipe. So here, right here, kind of shows you a through component resistor, and this here is the symbol for the resistance, and then this would be the analogy used in fluid or water flow. So essentially the water is flowing, and then there is a restriction which causes, which kind of opposes the flow of water. The equation for the voltage, basically as the current flows, there is a voltage drop, or the electrons or the current that's flowing actually loses some of the energy, and there is a voltage drop, and this voltage drop is given by V equal to IR, which is basically known as Ohm's law. So This is not really used as much in electronic circuit, but it's a little bit important to know. Typically when you take resistance and connect them together, they're known as connecting resistance in series. Resistance in series, the total resistance increases. The effective resistance is given by R1 plus R2. So it's similar to putting kind of a restriction in series. So essentially, if the first one opposes current by an amount X, the second one opposes the current flow by an amount Y, the overall opposition basically becomes the sum of the two. When resistance are connected side by side, they are known as connection in parallel, like the diagram shown here. Basically, when resistance are connected in parallel, the total resistance actually decreases, and the inverse of the total resistance is given by the sum of the inverses of the individual resistance as shown below here. So this is similar to having a pipe with the resistor connected like so in parallel. So since the actual water flow has two parallel paths to go through, the overall resistance it will encounter actually decreases, because if there is more resistance here, a lot more of the flow can actually go here, and if there's more resistance over here, the lot more of the flow can go to the other side. So where is the resistance typically used? So we could use a resistance to create a voltage divide. So remember where we talked about the resistance being in series, the total resistance adds up. So imagine there is an input voltage V in, and then we have two resistance connected, and then we measure the voltage V out at the midpoint or the connection point between the two resistors. So the current through the circuit here would be given by V in divided by R1 plus R2, and then V out is basically going to be the voltage drop across this resistance, which if you recall is given by current through the resistance times this value of the resistance. So what we end up having is that the V out is going to be R2 divided by R1 plus R2 times the input voltage. So essentially what we're doing is taking the total input voltage and dividing it between the two resistors. So this type of arrangement is known as a voltage divider. So based on the values of R1 plus R2, we can get different values of the output voltage, and if R1, in the special case that R1 is equal to R2, then the output voltage is going to be exactly half the input voltage. The other uses of the resistance is when we want to restrict the total current that is flowing through our load. So assume there is some voltage here, this is V in. What we do is we have a load which can only take, say, a resistance of, so it can only supply or take, say, 1 amp. So what we'll do is, if you know the voltage of the load, we can calculate that the resistance that would need to go over here using the formula R would be V in minus VL divided by I load. So if we do this, what will happen is the voltage across the load would be VL, and the difference V in minus VL would be dropped across the added resistance that we add. The other use of resistance is to typically pull up or pull down a lot of our electronic circuits. So this would basically be given by our data sheet or in the data sheet, and they tell you need to use a pull up or a pull down resistance of so many ohms or so many kilo ohms. So what typically happens is when we have an electronic component like this, if there is nothing connected, sometimes it's known as a floating terminal, which basically means that there is nothing connected, and the output is going to basically be random noise, which the thing would basically generate. So if we connect this to some kind of a measuring device, we'll notice that the output is actually kind of like changing randomly, like shown here. And this is not very good because it could potentially cause a lot of problem in rest of the circuitry. So typically what is recommended is that you connect a resistance from this terminal either to the supply voltage, the positive of the battery, or which is known as a pull up resistance, or what we do is we pull down, where we actually connect this to the negative of the battery through a resistance, where if there is no voltage being supplied by the component, the output of this particular terminal is going to be pulled down to 0. So when the component actually starts supplying current, the output, it will basically supply enough current to make sure that the voltage drop in the resistance is overridden and it actually produces the required voltage. So the typical values that would be needed for the pull up and pull down would be given to you in the data sheet for the corresponding component. The next component we'll be talking about is the capacitance. So capacitance actually is a parallel plate capacitance, basically stores charges between the two plates. Essentially it consists of two metallic plates and a little bit of a gap here. This is the normal parallel plate capacitor, and the one on the right is known as an electrolytic capacitor. So again, we cannot go into too much detail about either of these, but basically the actual equation and the concept remains the same. If you think of it as analogous to a storage tank, where basically water goes in, and then as more and more water goes in and gets stored, the voltage, which corresponds to the height of this water, keeps increasing. So the actual voltage across the capacitance is proportional to the charge, and the actual value is given as V equal to 1 over C times Q, where Q would be the charge, which if you convert, the charge is going to be the integral of current over time. We basically get the formula V equal to 1 over C integral I dt, or we can say I equal to C dV over dt. dV over dt is the rate of change of voltage. So what this does is that the capacitance kind of has a derivative component. So this is typically used to remove fast ripples. So essentially, if you have a component like this and then you connect a voltage, a capacitance, the output voltage is going to be much smoother. So essentially, imagine there is, for some reason, this is not a very ideal battery, or maybe you're connecting it on and off. So the actual voltage that's coming in has a lot of ripples. If you connect it to through a capacitance, basically put a capacitance in parallel, the capacitance is going to absorb a majority of these ripples. Again, the amount the capacitance can actually absorb, it depends on the value of the capacitance as well as the magnitude of the ripples. So obviously you can't completely get rid of all the ripples, but for the most part it will be much smoother. The other use of a capacitance is known as a low pass filter, which is kind of similar to a ripple remover. Essentially what happens is if the voltage changes very slowly, then this output, which you measure across these two terminals, will be equal to the input value. If the voltage changes very quickly, the capacitance is going to absorb all of the voltage and the output basically goes to 0. The next component that you'll encounter is known as an inductor. Inductor basically stores magnetic energy. So it stores the current flow energy, and then it is analogous to a paddle wheel. So if the rate of flow of current tries to decrease, if the rate of flow or the rate of current tries to increase, what tends to happen is that the paddle wheel begins to rotate faster. As a result, it takes energy from the flow, and so it causes a potential drop. If on the other side the current flow tries to decrease, then the paddle wheel actually provides energy into the flow, thereby it produces a positive voltage. So the inductor, the voltage across the inductor is proportional to the negative rate of change of current. So we can give V is equal to minus L di by dt. I apologize, I missed the minus sign over here. So this is a continuation. So what happens is typically when you use an inductor, so what happens is you can basically set up a circuit like shown below. So when the switch is closed, the current basically flows through the inductor, and the inductor basically gets charged, or it stores magnetic energy. And then when you flip, the switch opens, the inductor still wants to drive a current. So here there is a little bit of a gap between these 2 points, and the inductor wants to basically drive the current really badly. So it starts to produce a huge amount of voltage. So when you basically have a very large amount of voltage, you basically can produce a spark between a small gap. So this is basically used in the spark plug of an internal combustion engine, and the same thing is also used to start the it's used in the ballast of the compact fluorescent light as well as the longer fluorescent light that you find basically in the industries or maybe even in your home. So far what we looked at were linear components, which basically means that if I double the voltage, the current basically is going to get doubled. So they're going to respond linearly to change in the input. Now we look at diode, which is the first nonlinear device. So what the diode does is it allows the current flow only in one particular direction. So it would be analogous to a flow control valve. So essentially this would be the symbol of the diode. Basically current will flow in the direction of this rectangle over here, and basically the left side would be the positive anode and the right side is the cathode, and then this would be the symbol of the different types of diode that you would encounter. So essentially what will happen is, if you connect the diode in the forward direction or you forward bias it, it will allow current to flow through it. And so if you connect it at a load or a bulb, that will glow. And then if you connect the diode in the opposite direction, it's going to block the current completely, and so this bulb wouldn't glow. Obviously it looks rather stupid as to why you would use a diode in this format. So we kind of reasonably quickly look at why and where diodes are used. Before we do that, we take a look at light emitting diode, which is basically a variation of diode. Which basically emits light when it's turned on. So basically when you forward bias LED, it actually emits light. When you reverse bias it, it basically just blocks the flow of current as any normal diode would. Typically the voltage drop in an LED is 1.8 to 3.3 volts. The 1.8 is for a red LED and 3.3 is roughly for a blue LED. The light frequency, the actual voltage drop roughly increases with the actual light frequency. The brightness of an LED is controlled by the current flowing through it. So the higher the current rating of the LED, the brighter it's going to be. And typically you would find LEDs in the 2 milliampere range, 10 milliampere range, or 20 milliampere range. So these are common values. So then the question becomes, how do you actually use an LED? So I've kind of already given you the hint. So what you need to do is you might typically need to use a resistance in series. So for instance, imagine you have a white LED which typically requires has a voltage drop of 3.5 volts, and then you wish to power it from a 6-volt battery to limit the current to 10 milliamps. So the current is basically the rated current to this LED. And at this point you can kind of pause this video and then think about this a little bit. So the basic idea is how do you bias this LED. So you can kind of scroll back to this video where we discuss about using resistance in series and how you can use it to limit the current or limit the voltage through the load. So what we basically do is, if you connect the resistance in series, we want to supply 6 volts and the LED only requires 3.5 volts. So we need to drop 6 minus 3.5 volts, which is 2.5 volts. And the current the current flow that's needed is 10 amps. So we basically need to drop this 2.5 volts for a current of 10 milliamperes. So if you put this together, we can find that the resistance is 250 ohms. If you want to look at more information on LED, so I recommend the Wikipedia site, which is basically wiki and then LED_circuits, or you can look at the second website, which is theledlight.com/LED101, which basically gives you the real basic concepts that's used in LEDs. Anyway, so coming back, so where would you typically use, if it's not an LED, which basically gives you light, the question then becomes, where would you use a diode? Typically the diode is used on sensitive components to prevent like accidental reverse voltage, and they can also be used to rectify AC, which is basically a fancy term to discuss about converting AC to a DC voltage. So generally what we use is known as a full wave rectifier. So the circuit basically uses 4 LEDs numbered 1, 2, 3, 4 here, and the input is basically going to be a sinusoidal voltage, and the output is going to be kind of like the voltage in the same direction. So when the input voltage is positive, shown in red here, the diodes 1 and 3 conduct. So essentially current flows from here, flows through 1, goes all the way here, and then it goes through, we are assuming there's going to be a load or a battery or something over here. It goes through the load, comes back to the negative, flows through the diode number 3, and then flows back to the supply here. If the voltage becomes negative, so basically that's going to be the second half of this signal, basically shown here in blue. What happens is the current basically is going to be flowing through this path, and then it's going to flow through the diode number 4, goes to the load, goes to the negative here, and then flows through a diode 2 back to the supply. So notice that the diodes 1, 3 and 2, 4 conduct in pairs, and irrespective of which pair of diodes are conducting, the supply or the voltage in this part of the circuit, the output part, is going to always be positive. So this is known as a rectifying or a full bridge rectifier. So the next component we will discuss is known as a transistor or a bipolar transistor, and it's usually shortened to BJT. So a BJT is used to amplify the current, or it actually acts as a switch. If you wanted to know a little bit more about these, you can refer to the Wikipedia article, but what happens is they typically have either an NPN or a PNP transistor, and the reason transistors are famous is because this was from a way back. They basically help shrink the size of a lot of the components by a large amount, and if you look at any integrated circuits, they basically incorporate hundreds and if not thousands of these transistors into a single component. So the next thing we'll discuss is integrated circuit, which is where things get significantly more interesting. The actual side of the circuit that we showed here, like these little ones, even though this appears bigger, all of these actually have a very, very tiny amount of active material of silicon that's actually used. So what that means is you can put hundreds and even thousands of these transistors or other semiconductor devices and fabricate them onto a single chip. So that's what is meant by an integrated chip or an IC. So if you look at this chip, it might potentially have like 100 semiconductor devices, so like transistor, MOSFETs and so on. And this one, you notice that has significantly more number of pins, and basically this will be even smaller. So your PCB would basically have these integrated chips, and you put a bunch of resistances. These would be your capacitances. Same thing here. So this would be an integrated chip. These black ones would be the resistances, and you'd have some capacitance like here and here. And then you put them all together, and then you form the actual circuit. So what needs to happen is that the IC would get connected to the external world using or through these pins over here, and then you put like wires would correspond to this, and the data sheet provides the pin out, which provides cross reference between the pins on the IC with the function and as well as what needs to be connected to those particular pins. Basically, if you look at kind of like schematic or a simplified version of the chip, you typically would see something like this. The through component chip, which is basically the larger one, either has a notch here or a hole. Sometimes it has both, which basically helps you determine the bottom left corner. Same thing if you have a surface mounted component, which is much smaller like so, and then you have these would be the pins, which looks like tiny wires or tiny legs. The circle would help you determine the bottom left corner. So once you can identify the bottom corner, the first pin is going to be this. For the through mount, it's going to be this is going to determine pin number 1. For your surface mount, this is going to be pin number 1. Then what you do is once you locate the pin number 1, you start counting in the counterclockwise direction. Sorry, this should be counterclockwise. Basically you go like so. Essentially go 1, this would be 2, 3, 4 and so on. So this would be 1, 2, 3 and so on. And then once you get, so you can basically number the pins like this. So you get 1, 2, 3, 4, 5, 6, and then basically you number this 1 through 8, 9 through 16 and so on. What we're going to do is really quickly look at some example, basically a single example data sheet. If you wanted to get more information, we're going to look at the 555 timer data sheet. So if you wanted more information, you can look at the Wikipedia article for the 555 timer, which is this link over here, or you can look at the data sheet for the LM555, which is the data sheet we're going to look at right now. Okay, so if you look at the actual data sheet, so you notice it looks kind of a little bit scary at first. Typically what happens is it is going to give you all the information that you'd be needing to use that particular data sheet. So it will tell you the features. So this is going to be saying that, okay, hey, by the way, this LM555 is a direct replacement for some SE555 and NE555. At this point, you're probably not concerned. The timing, it says, ranges from few microseconds to hours. Both operates in this. It can say it can source this or syncs this particular value. And then it says what the output is, what is the temperature, and so on and so forth. Next, they typically give you the application. So this is for timing, and then here it describes the particular what the particular chip does, and they give you a schematic. So these are actually schematic of transistors. Notice that it looks a little bit scary, so we're not actually going to look at the schematic unless you are actually designing a similar chip. So you can go through it. It'll give you like the revision. But what we're mainly interested in is basically looking at the pin configuration as well as specification and like the sample application. So this, if you notice, gives you the schematic of the pin. So notice that they're numbered. So this is the notch. So if you kind of had turned it around, this would be the left corner. In this view, this gives you 1. It tells you, okay, 1 is ground. It needs to be connected to ground. 2 is trigger, 3 is output, 4 is reset, so on and so forth. It kind of gives you piece of information here as well. The next, typically they give you the specification, so they give you the absolute maximum that the chip can withstand, which basically means what is the maximum voltage and the temperature you can supply to the chip before it actually blows up. Then they give you the electrical characteristic and then like some frequency characteristic that's used, and so on and so forth. Next, it'll kind of give you like the functional blocks that's available in the chip, and then the most interesting thing for us is kind of the sample application. So they tell you the device can operate in the following modes. The first one is a monostable, and they tell you that if you wanted the monostable, what you need to do is take this chip, connect the 1 to the ground, put a capacitor over here, connect these two together here, put a resistance over here, and then supply to the supply voltage, which is known as VCC. And then they tell you if you do this, you can calculate the time as 1.1 RA times C, and this is what you can expect to see if you measure different voltages. And they talk about connecting it in A-stable mode. So they basically give you the typical kind of for an LED flash. So they basically tell you if you take this chip, connected these two together, this is, if you notice, it's actually connected slightly differently, and then do all of this. This will allow you to calculate the frequency, and then what you can do is you will basically expect to see something like this, kind of which oscillates between on and off. You can download this particular chip, kind of the data sheet for this particular chip, take a more detailed look, and then see if it makes sense. Yeah, so this basically concludes our video on basic introduction to electronic components.